This is part 2 of the video series where I go through calculations for the capacitance of different types of capacitors. In part 1, we talked about the general idea of what we're trying to do, and we found the capacitance of the parallel plate capacitor. And the method was first find the electric field, usually based on using our understanding of Gauss's law, and then use our knowledge of the electric field to find the potential difference, and that involved an integral, meaning a sum of the changing potential of each tiny step as you imagine walking from the one point to the other point, from one side of your capacitor to the other. So here's another example. This is the example of coaxial cylinders, or you might think of it as a coaxial cable. Coaxial means that they have the same central axis. So we imagine you've got two cylinders. It doesn't matter if the inner one is solid or like a pipe or something. The outer one certainly has to be a pipe. But the inner one could be solid, or just it's of a smaller pipe with all the material on the outside. It doesn't matter, right? It's an inner one and an outer one. So they're going to have inner radius R in, and outer radius R outer. I try to draw it in 3D here. If it looks confusing, here's the top view. Imagine as if it looks straight down from above. I see kind of a cross section. This is the inner cylinder. Here's the outer one. And I imagine if we charge Q spread out evenly over the inner cylinder, and minus Q, the opposite but equal charge on the outside. That of course means, because the outside cylinder is bigger, that the charge density, like per area of wall here, is going to be less than here, because it's just more area for the same total charge. And actually, I'm going to change this up a bit, because for this kind of setup, if you imagine with a long cylinder that keeps going, I can't draw it to be infinitely long, but if you imagine it's going on for a very long time, it's probably more useful if I talk about the charge per length. So I'm going to replace my positive charge with a positive charged linear charge density, and the outer one with a negative linear charge density. Alright, so lambda is the linear charge density. That's how many coulombs per meter of cylinder length. Right, so that is the how many coulombs per meter, say, right, per unit length cylinder. And as a result, what I'm going to find in the end is the capacitance per meter of this setup, right? If I've got a cable of 3 meters long, well, I'm going to find the capacitance per meter of coaxial cable. This is a real cable with an inside and outer, like a core on the inside and a separate conductor on the outside. There have to, of course, be some material, some insulator separating the two, so they don't just touch. But that doesn't matter for our purposes right now. Right? We imagine the setup of cylinder in the middle, cylinder on the outside. And you've got lambda is what tells us number of coulombs per meter length of this setup. So, what's the electric field? Now, you've studied that kind of example before with cylindrical symmetries, and you hopefully remember that the electric field in this case is just going to be radially outwards, right? So, see if we can draw this in 3D here. Sort of meant to be radially outwards like this, and you know, the same thing is of course true down here. It's going to be harder to draw. Not sure if I'm doing a very good job here. And then in the back, hardly. You get the idea. If I draw it from above, it's probably clearer. When I get electric field lines, it look like this. A lot easier to draw. Right, because the inside, I'm assuming the inside here is positively charged. If it's not, if it's negative, well, I'm just going to flip the direction of the field lines, because reversing the charges just makes them just flips the direction. There's no electric field outside it. Again, you can prove it with Gauss's law. Right? You imagine a cylindrical Gaussian surface, and the total charge inside is going to be 0 because there's as much positive as there's negative. So there's only field between the two from going from the inside outwards. Right? This is my E field. Now, you apply Gauss's law to say a surface that's sort of does something like this. I just my Gaussian surface, or in here I might take a Gaussian surface that's sort of it's cylindrical, goes behind the inner one, has a certain radius r from the middle. Try and draw this in 3D, right? Really hard. R. Then you've done this example before, right? You understand there's no flux to the top, no flux to the bottom, just out the side. And the answer you're going to get for the electric field strength is going to be the charge density divided by 2 pi epsilon 0 times r, where the little r is the distance from the center. What that means that you divide by r is that the further out you go, the weaker the electric field gets. Right? That makes sense. You can see that the field lines out here are further apart than they are in here. Right? Here they're just closer together because going around them, around the cylinder is less distance. Right? Over here they're more spread out. Okay, so we know that if you don't remember the derivation of this, if you can't remember how to apply Gauss's law here, go back to an earlier video or your notes. Right, this is the electric field. Now we've got the electric field, we're going to find the potential difference. Right, defining delta V. Now delta V is the integral of the E field along the path. And what I did not do in the first example, I'm not going to do here either, is worry about the sign of this. Right? Because I just want to know how many volts. I know that the inner one is the higher voltage, the outer one. When I get a positive number, I know I've gone down that amount, the number of volts, as I've gone from here to here. So let's pick our path. Now you could pick any path. I have to say this, right? You could start here and go some kind of strange meandering path around until you end up on the outer plate. The math would still work out. It's just you sort of get positive and negative contributions. It's like you're going down a hill, but you keep going in circles and make some shapes on the side of the hill before you end up at the bottom. Still gonna have lost the same amount of altitude in the end, but the calculation would be a lot harder based on that path. So we're going to pick the easiest path. Right? And the easiest path is going to be, we're going to start in the on the inner cylinder and just go in a straight line radially outwards. So our little steps, our little ds steps are going to be this way. It's our integration path. So integration is from the inner cylinder, right, abbreviated, to the outer cylinder. So what's the sensible variable for our integration to choose? Well, because we're going along the radius, r is what's changing. We've got electric field in terms of r, so that's the only sensible choice here. Right, to actually evaluate this, we're going to plug in what the electric field is. My electric field strength. Notice I don't have to worry about the direction, because by going radially, I'm always going along the electric field line. So the angle between my path, my step direction, and the electric field is 0. So the dot product is just it just involves multiplying the magnitudes of the two quantities. The cosine of the angle between them is 1, because the angle is 0. Okay, so this, and then I'm changing my radius every time. That is my path. And I'm going from the inner radius to the outer radius. Now I look at this, most of these are constants, right? Lambda is just, you just assume there's a certain amount of charge on the cylinder. 2 pi epsilon naught, constants. Okay, but there's a 1 over r. Let's rewrite this. It is integral. I'm going to take out the constants, lambda over 2 pi epsilon naught. And the actual integral to evaluate is between r in and r out is just 1 over r times dr over r. So what is this? Now this is where you've got to go to your calculus course. What is the integral of r? If you're only taking calculus right now, calculus 2 right now, you haven't really done much integration yet. Ask yourself, what function differentiates to become 1 over r when differentiated? Like the derivative of what function is 1 over r? Because you did that in calculus 1. And hopefully remember that that's going to be the log, the natural log of r. So what this gives me when I evaluate is the constants out front, they just stick around. Then I'm going to get the log, natural log ln of r evaluated between the inner and the outer radius. Just plug those in. I'm actually starting a page here, so I don't run out of space. So we get that delta v is lambda over 2 pi epsilon 0, and then log the outer radius minus log of the inner radius. And in a sense, if you leave it like that, I think that's kind of okay. But really, it doesn't quite make sense, right? ln, can't read this. It doesn't quite make sense because this is a quantity that is in meters, or some unit of length. Taking the log of a meter doesn't really, I mean, what is that? What's the log of a meter? Is it different from the log of a mile? It isn't really defined. I mean, you can sort of do math with it, but it doesn't really mean anything. So let's rewrite this. Now, these are log of one thing minus log of another thing. Hopefully, you remember how to deal with this. But we can use the rules of logarithms and write this as the fraction the outer radius over the inner radius. Now, because the outer radius is bigger than the inner one, it has to be, otherwise the setup doesn't make sense, right? I mean, this circle has to be bigger than the inner one, otherwise it wouldn't be the outer one. That means the thing inside the log is bigger than 1, which is good, because that makes the log positive. Okay, so we've got our delta V, and now we want the capacitance. The capacitance per length, per meter, say. So C per length of cable is going to be delta V per charge per length of cable, right? C is delta V over cube, so if I divide by the length of the cable, I guess I could write it like this. Of course, the more convenient. Sorry, wrong way around. What am I doing? Excuse me, ladies and gentlemen, I've clearly lost it. Q over delta V, the charge per potential difference, that is the capacitance, divided by the length. So you get the capacitance per length. Of course, I mean, you can just rewrite it as Q over delta V times L, and Q over L, right, that is nothing but lambda. So I get that the capacitance per length is just lambda over delta V. Now if I rearrange this equation, delta V is equal to this, I am going to get 2 pi epsilon 0 multiplying, divide by delta V, take this over, this goes over, so I've got to divide by the log of R outer divided by R inner. That's my expression for the capacitance. Notice again, this quantity does not depend on anything other than the geometry, right? The two radii, the outer radius, the inner radius. It doesn't depend on the charge you put on it. I double the charge, double the potential difference, hence no change in charge per potential difference. Because in all those cases, charge and potential difference are linearly related, right? Delta V is something times lambda, not lambda squared or lambda cubed, not square root of lambda, no. This is linearly related to this or linearly related to the charge Q, depending how you want to express it. Okay, so this is my capacitance per length for the coaxial cable. Okay, let me now introduce two more problems, two more examples, where I'm not going to go through all the steps. I'm going to leave it for you to figure it out. The next example are cocentric spheres. Right, so imagine you've got two spheres and you've got one inside the other, and realistically, right, you have to, it can't be a perfect sphere, the inner sphere must be somehow like attached. But maybe you can suspend it from some insulating wires from the outer sphere or something like that. But what you have is an inner sphere, an outer sphere, and the inner sphere has some radius r inner, the outer sphere has some radius r outer. Let's assume the inner sphere has a total charge Q plus Q, the outer sphere has a total charge minus Q. Now, you know what the electric field looks like in this case. If not, you can apply Gauss's law, right? But you've done that very example. Maybe with arbitrary charges, but that doesn't matter. In this case, the electric field is going to look like this. Now, don't confuse it with the cylinder, right? In this case, it's really, imagine this is kind of a sort of spiky ball on the inside with spikes going in all directions, not a long cylinder with spikes going sort of radially outwards, right? You can imagine spikes coming out of the page towards the camera here, for example. So it's kind of a spiky ball on the inside. There's no electric field on the outside. Again, you can prove it with Gauss's law, right? Imagine a big Gaussian surface, spherical surface around it. The total charge inside that is 0 because we've got plus Q inside, you've got minus Q inside. But as long as you're between the two spheres, the inside of the bigger one, a spherical Gaussian surface here is going to have some charge on the inside, some charge enclosed in it. Now, what's the electric field strength inside? Well, it's not no big secret. Q over 4 pi epsilon naught r squared, right? That's just Coulomb's law, really. Except because it's a sphere, it's not a point charge, but we've proved in the past using Gauss's law that you get the same result as long as you're outside that inner sphere. So the first part in these calculations, finding the electric field, is usually something you've done before when you've worked with Gauss's law. So now I want to find the potential difference. So delta V is, we imagine, taking little steps, and the logical steps to take, right, is to just march along one of those field lines. If you go some other angle, you can still do it, it'll just make the calculation more complicated. You're going to get the same answer though, right? The delta V does not depend on the path taken. That is why the concept of potential exists in the first place. It has to do with the electrostatic interactions being conservative interactions, conservative forces. But we'll make our life easy by marching along in our tiny little ds steps, right? We'll march along from the inside to the outside. So let's set up the integral. We're going to go from the inner sphere to the outer sphere. Those are the limits of our integration, the ends of our path, our starting point, our end point. We're going to get E dot ds. Let me set up this integral for you. Well, we're going to again use the radius, the distance from the center, as our integration variable, right? And again, the electric field falls off as you move out. In fact, it falls off faster than with the cylinder. It goes as 1 over r squared rather than just 1 over r. Last example, it went as 1 over r, and we can always visualize that based on how the field lines spread out. Here they spread out both in sort of this direction, but also in the sort of up in this direction, right? Like in the third dimension. Whereas with the cylinder, they didn't spread out because there was more cylinder above and below. Whereas this is just a sphere in a single spot. So the integral is going to look like we're going from the inner r to the outer r. This is the electric field. Our step is just a step in a small change in radius, and we step in the same direction as the field. It's a choice we make, but it makes our life a lot easier. It's the only sensible choice, really. So the dot product just becomes the magnitude times the magnitude, because the angle between the two is 0. Okay, now this is an integral you can evaluate. When you can evaluate, you can plug in the values and work through the same steps we worked through in the last example. Of course, this goes 1 over r squared, so you're not going to get the log as the answer. But again, if you're unsure because you haven't done enough integration yet, you don't really understand yet, you know, how to actually evaluate integrals for every single type of function. Remember, the way to figure out what is the integral of this is, well, first you take all the constants out front. They don't matter. They just multiply everything, and then you ask what function differentiates to 1 over r squared. You figure it out. You plug in your limits, and what you're going to find. I think I'm going to leave those steps to you. Write it out. Your work here. End up finding that the capacitance, the charge held per potential difference, is 4 pi epsilon naught the inner radius times the outer radius divided by the difference between them. Right, and it's your job to prove that. Right, prove it. Started you off, right? So you really just have to evaluate this, and you should find that that is the answer. That's another type of capacitor, right? You've got one sphere inside another, sure, held in place somehow. It's not just hovering there. Maybe there's a little sort of insulating stick here that holds it in place. Who knows, right? Doesn't matter. This is our setup. This is the capacitance you find. Again, it just depends on the geometry, right? The distances, the radii, not the actual charge. How much charge you put on it, okay, that's up to you. That will determine the potential difference. But the capacitance itself is just a property of your how you arrange those spheres. Okay, let's do one more quick example. That example, again, I'm only going to set it up for you. It's just 2 spheres, and there are of course other examples you could be doing. Right, these are just some of the sort of simpler ones. So imagine I've got a sphere here. Maybe it's held in place somehow on some insulating stick. It has charge plus q. It has a radius r. And then I'm going to have another sphere over here. Let's pretend they're identical. This makes our life a little bit easier. Could do it for non-identical spheres, one bigger than the other. Go for it. I'm going to assume they're identical just to make our life a tiny bit easier. And we're going to assume that their centers are a distance d apart. So you want to find the potential difference between this point here and this point here. Right, between here and here. What is the potential difference? And then you can find, once you know that, you can find the capacitance. Right, C is Q divided by delta V. So how do you find delta V? First, we're going to find the electric field. How do I do that? So in this case, I can't really use Gauss's law on the whole setup, right? Because it's not, I mean, there are two spheres. If I sort of moved, like, I can't like spin it. It would change the, the setup. If I say, you know, I try to rotate this whole setup by some angle, okay, things look different. This is not nicely symmetric. But you know the electric field due to each single sphere, and then you just add them. You know the electric field is going to look something like this, right? It's essentially a dipole. Right, so E is going to be equal to electric field contribution due to the left sphere plus the electric field contribution due to the right sphere. Now, in general, this is you know, at least a 2D, really a 3D setup. So the electric field here is some vector addition, the kinds of examples you did early on in the course. But let's just pick our path of integration, and I think we all agree that the easiest thing to do would just be to sort of march along here in a straight line, always along the electric field line. If you go along another field line, you can do that, but it's going to be curved, it's going to be harder to express. This is easy, it's going to go along a straight line. Also, in case you're worried, if those are conducting spheres, the potential is going to be the same everywhere on the sphere. So that's not something to worry about. Okay, so you march along from here to here in tiny little steps. So how are we going to express that? Well, the electric field, well, you probably want to put down some coordinate system. So you might want to call, let me plot it again down here, sphere 1, sphere 2. Might say, okay, this is my x equals 0 here, and then I'm going to go x direction. This is x equals d. Now be careful. You're starting not at x equals 0. You're starting on the surface here. You can figure out what that initial x variable is, and you end up not at x equals d, but just to the left of it. Right, so this is where you're marching along, from one side to the other. And that will determine your limits. Right, this is your lower limit of your integral. And this is the upper limit of your integral. Those x values. And then your chosen path is just a change in x. And it's in the direction of the field, so we're making our life as simple as possible. The one challenge you still have is to actually, work out what this is. And you've got to be careful here, right? Because it's not just, well, the left one, that's just going to be q over 4 pi epsilon naught x squared. You write this down just because I'm feeling generous here. This is going to be q over 4 pi epsilon naught, 1 over 4 pi epsilon naught is just k, right? Times x squared, because x is the distance from the center of the sphere. Notice that the value of your x position, right, x equals 5 here, that doesn't mean if this is x equals 5, 5 is not going to be your distance from the center here. So you want to first express the distance from the center of this sphere in terms of x, and that's the thing you plug in here in the corresponding expression here. So think about this, figure this out, and then you want to integrate to find delta v. When you got it, the integration itself isn't hard. Again, you can do it sort of by inspection, like intuitively asking what function differentiates the function I got. Right, so you know the steps. Look back at the other examples to figure out what you have to do here. And then you find that the final capacitance, right? So here again it's your turn. Same thing up here, your turn, right? You find all said and done that the capacitance is going to be 2 pi epsilon 0 times dr minus r squared divided by d minus 2r. So d is the distance from center to center, r is the radius of the spheres. Again, it's just a geometry. How big are they? How far they are apart? Right? So again, your turn to prove it. Prove that this is indeed the expression. I've given you enough of a setup that you can work that out. Okay, do a little sanity check here. D, the distance center to center, better be bigger than twice the radius. Otherwise, the sphere would sort of be inside each other. Right? I mean, if this was smaller than this, then it'd be like this. That doesn't make any sense. Right? So this is, the denominator here is positive. Just a sanity check on our final answer. Also, the numerator is positive because d is bigger than r, so dr is bigger than r squared. But see if you can derive this, right? Figure out, you've got the electric field for the left one, figure out the electric field for the right one in terms of x, and then you can perform the integration to find delta v. If you can do this, great, it means you've understood how to find capacitance, how to calculate potential difference from field, and so on. So I hope this was helpful. Please fill in the gaps in the last examples. You do learn a lot by actually doing it. Even if you listen to everything I said and it makes total sense to you, just take a couple of minutes to sit down to actually go through the motions yourself. Maybe re-derive the results I had earlier to make sure you actually understood it and you remember it. And if you really, if you've got a grasp of all of this, you're really in good shape to understand the full topic of electrostatics as much as we're going to cover in this course. Well, good luck with your studies, and I'll see you in my next video.